Hello, so we will wait for a few minutes if others want to join, and we'll start in maximum 5 minutes. Hello everyone. So, am I audible? Please confirm yes or no.
Yes, yes, miss.
Okay, thank you. So, welcome to week 6 problem solving session, Saturday 3 p.m. Today we'll be solving a few problems in quantum mechanics as already started by Professor Amal Kumar Das in your regular classes. So, our first question being, yep, so this is a 1D potential problem. So you have a particle starting in a linear combination of two stationary states. So what is the wave function at psi xt at a later time? Please try to solve it and let me know. What is a stationary state? Why did they specifically mention that it's a combination of two stationary states? What does this mean? Anybody? Okay, so you know that the Schrodinger wave equation, which is psi xt e minus I e t by h cut, where E is the energy of the system, right? So yes, the wave function itself does not obviously depend on, I mean, it does depend on time. You can see this time factor, but the probability density, okay, how do you find that? Psi xt, the conjugate, and just this multiplication of these. So basically this, right? So first, what will this be? What will be psi star? So look at this one, EIET by H cut, and just psi. Um, this psi is like this. Okay, so psi star psi, let me write it like this. Okay, so this multiplied by minus. Okay, so you can see these two cancel out. So basically it's just the x part, okay, which does not depend on time. The wave function has two parts, right? A space part and a time part. Okay, so yes, the wave function has a time dependence, but its probability density does not. Okay, so the probability density does not depend on time. Okay, so the same thing happens also in the expectation value of any dynamical variable. Okay, so let me write this. In the expectation value of any dynamical variable. Okay, so anyway, yes, so this is a stationary state. This is just the definition. I mean, I just explained what I meant by stationary states. Now you will tell me so that what is the wave function at psi xt at a later time. This at won't be there, so what is the wave function psi xt at a later time? How will you do this? So just the x part is given. Okay, the space part, the spatial dependence. Just this is given. So what do you think the wave function will be at a later time? Nothing, just if you have to write the bigger psi, like including both space and time dependence, then this wave function will be just, I'll just add the time dependence plus C2 psi 2, oh sorry, it won't be x1, just x, e minus ie2 t by h cut. That's it. Nothing, I've just added the time part. But yes, you have to remember, you have to write E1 corresponding to psi 1 and C1, and E2 corresponding to psi 2 and C2. Probably this is for n equal to 2, combination of two stationary states. Okay, so E1 and E2 are the energies which are associated with psi 1 and psi 2. Okay, and then find the probability density. What will that be? Yes, as I've already written here, this is the formula for probability density. Okay, just psi star psi. So same here. Probability density will be just square of modulus of this. So basically just this. Okay, so let us first write this one, psi star. Okay, so what will that be? C1 psi 1 e, this is minus, so I'll write plus. Okay, same for the next state. Okay, done. Now just psi again. Okay, that's it. Now yes, you have to sit and multiply this. So let us multiply the first two terms. C1 square psi 1 square, and e, the exponential terms cancel out, and then let's multiply the first and the fourth terms, plus C1 C2 psi 1 psi 2 e minus I. I'm just writing it in this form because I want to subtract the smaller energy from the higher one. Okay, now the second term and the third term, C2 C1 psi 2 psi 1 e raised to the power I e2 minus e1 t by h cut. And then again these two cancel out. The second and the fourth one. So c2 square psi 2 square. Okay. And then what you end up with, now this term and this term, you can use Euler's formula, which is E I theta is equal to cos theta plus I sine theta. Okay. So this will finally give you c1 square psi 1 square plus c2 square psi 2 square plus 2c1 c2 psi 1 psi 2 cos e2 minus e1 t by h cut. Okay, let me know if you've got something else. Okay, so you can see that the probability density is oscillating sinusoidally, okay, at an angular frequency of e2 minus e1 by h cut. Okay, so here you see it is not a stationary state because the probability density is dependent on time. Okay, so this, let me write in red, not a stationary state. So individually they were, but when they're combined together linearly, then it's not a stationary state. Okay, so this is my answer to part B. Is there any doubt in this question? If not, let's go ahead to the next one. So calculate the expectation value of x, x square, momentum, p square, sigma x, sigma p for the nth stationary state of the infinite square well. Is the uncertainty principle satisfied? Please try this and let me know. You must be knowing, you must be knowing that the the wave function for the infinite square well is given by this. In this problem solving session, I'm not showing you the derivation of these because I think these have been very rigorously done in your theory class. Okay, so let's just go ahead, start directly with the formula and just basically try to understand what the problems want. Okay, so this is the wave function of the infinite square well. You know, V is infinite. Once stuck in, the particle can never come out. Okay, it can never come out. But you know, the only possibility for a particle, if it is stuck here, to be on this region is by tunneling, right? Quantum mechanically that is possible, but this is not possible. Okay, anyway. And yes, the energy levels, which are discrete, are n square by square h cut square by 2ma square. Okay, this is just a reminder. Now, yes, go ahead and tell me what is the expectation value of x. Okay, as you solve, I'll start with the expectation value of just x. Okay, how do you find that? Right? So what does this give us? 2 by a x sine square n by x by a. Okay, of course this is 0 to a, so the integral bounds are from 0 to a. Okay, let us just take a substitution. Y is equal to n pi by a. So dx will be, so dy will be n pi a by dx, right? So our dx comes out to be a by n pi dy. So x0 means y is 0, and if x is a, then y is n pi, right? So a new integral is a by n pi whole square 0 to n pi y sine square y dy. Oops, sorry. Okay, that is equal to 2a by n square pi square, and then hope you're matching. If not, let me know immediately. Sine 2y by 4 minus cos 2y by 8. Okay, and this will go from 0 to n pi. So that will give you 2a n square pi square, and then n square pi square by 4 minus cos 2n pi by 8 plus 1 by 8. Okay, so this is 0, and solve this to find a by 2. Therefore, expectation value of x is a by 2. So a stationary state once again. Okay, so this is independent of the order of wave function, right? As in n is 1, 2 or 3, it doesn't matter. The x is independent of n. So that means, what I mean is, so you know how your first 3 wave functions look like? The first one looks like this, right? n1, if this is a and this side is x. The second one looks like this, right? 0 to a, this is side 2. N is 1 here, n is 2 here. And the next one looks like this. This is side 3, n is 3 here. So independent of the order, if it's in the lowest ground, is in lowest energy state, or the next higher one, or even a higher one, the expectation value of the wave function will always be a by 2. That means at the center of the wave, this one. Okay, this will always be the expectation value of x. Okay, so now what about x squared? What did you get for that? X squared. Let me write psi x first. It is 2 by a. Okay, I'll just write it here again. 2 by a, then sine n pi x by a. Therefore, expectation value of x squared, what will that be? Again, but this time multiply with x squared. What will this give you? I'm writing the steps for you. Just match and see you're getting the same steps. 2 by a, and then outside there will be a cube, and then again similar y substitution again. So I have here y square sine square y dy. Okay, so you are supposed to get 10 to a by square by n pi whole cube multiplied by y raised to the power 3 by 6 minus y cube by 4 minus 1 by 8 sine 2y minus y cos 2y by 4 0 to n pi. This further will reduce to 2a square by n pi whole cube, and then n pi whole cube once again by minus 6 n pi cos 2 n pi by 4. This will ultimately result in a square 1 by 3 minus 1 by 2 n pi whole square. Okay, so this is the expectation value of x squared. Okay, now expectation value of p, momentum. What will this be? Now instead of writing, you know, the writing momentum operator in terms of h cut and I, you can just write it like this, right? Because we already know what the expectation value of x is, which was a by 2. Okay, so m d by dt of a by 2 is 0, right? So this is our answer. So here you see that this is a stationary state, right? Because this does not depend on time. So that means the momentum is 0. That means nothing ever happens in a stationary state because your average momentum is 0. Okay, this is just conclusion of part of this exercise. Now expectation value of p square. Okay, so again just your like this, right? So I'm going to write it like this: h cut I d by dx square psi n dx. Okay, please put in the values. This is writing all this is taking up too much time. So you're supposed to get n by h cut by a whole square. Okay, just solve this for psi n is equal to 2 by a under square root multiplied by sine n by x by a. You're supposed to get this. If not, let me know. Okay, then you have these two terms. So sigma x okay, the square root of deviation. So what will that be? Square would give you x square minus this, right? Which you have already got. That was the whole point of finding out x and x square and all. Okay, so just writing these values. So x square was a square 1 by 3 minus 1 by 2 n pi whole square minus, and your x by 2 was a by 2, right? So this is supposed to give you a square by 4 1 by 3 minus 2 by n square pi square. Okay, so therefore psi x is what? Just the root of this, a square by 4. Let me just take this out. A by 2, 1 by 3 minus 2 by n square pi square. Similarly, for p, what will this be? Again, you have already solved this. So that will give you n pi h cut by a whole square. That results in sigma p being equal to n pi h cut by a. Therefore, our uncertainty principle, let us just multiply these two and we get here a by 2, 1 by 3 minus 2 n square pi square and n pi h cut by a. So this gives h cut by 2. You can take n pi inside, n pi whole square by 3 minus 2. Okay. So for say n is equal to 1, you have the product being equal to h cut by 2 pi square 3 minus 2. And if you solve this 3.14, just put 3.14 square. This is supposed to give you 1.136 h cut by 2. Okay. So that means sigma x, sigma p is greater than h cut by 2. Therefore, the uncertainty principle is satisfied. Okay. So that means you can never exactly spot the position. I mean detect or measure the position and the momentum together. Simultaneously, you cannot do that. If you try to do that, you lose out on either information. Okay, so let's go to the next one. A particle in the infinite square well has the initial wave function as given. So you sketch psi x0 and determine the constant A. How will the wave function look like? It will look something like this. Okay. Can you differentiate when do we write this psi and the small psi? This is a function of both x and t. Okay, so this involves psi x multiplied by the time factor e, whatever. Okay, time will be there basically. So whenever I'm writing capital psi, this will actually be capital psi, not small psi. This means both time and space are included. And if it's just a smaller one, that means I'm talking about only the space part, not the time dependence. Okay, so for say this is a by 2 and this is a and this is 0. So you can see that for x less than a by 2, there is a linear dependence. I mean just directly proportional to x. So this will just keep on increasing. And then beyond that, it's the opposite. Okay. So this is your psi x0 without any time dependence. And then phi psi xt. Okay, so this is similar to the problem which you've done just before. Okay, first you need to find, since this is your psi x0, you need to find a. Okay, and then psi n x comma t is equal to cn psi. This is just wait 1 second. E and then your time factor. Okay, so this, as you must be knowing that Cn, what is Cn? Square of this gives the probability that this wave function is in a state with energy En. Okay, so let me just write that. Gives the probability that psi nx is in an energy state with value En. Okay, so then you find Cnx and plug this value in this equation. That's it. Just needs good command over calculus. I mean integration, nothing else. Okay, so I will just put the final value, and when this will be shared with you, you can match. I'll put the whole solution in this, so you can just match if you got the steps correct. So your psi xt is supposed to give you 4 root 6 by pi square 2 by a summation over whatever minus 1 n minus 1 by 2 1 by n square sine n by x a, and then the time factor. That's it. Okay, so this is supposed to be your final answer, and the probability, this is B, and the probability of finding this particle with value E1 will be just C1 square. As I told you, this definition is the answer to the third question. Okay, that is supposed to come out as 0.9855. Okay, and the expectation value of energy is writing H for Hamiltonian summation of Cn square En, and that is supposed to give you 6h cut square by ma square. Okay, so these are the values that you're supposed to get. Please try to solve it on your own and then check out the solution when this will be shared with you. Okay, so let's quickly go to the next one. Yes, so now it's a harmonic potential oscillator. This starts out in the state psi 0 and psi 1. So find A. Basically just normalize it and find A. So I hope you have found out A by normalizing this. Just normalize psi x0, and what does that give you? Again, modulus whole square dx. This is supposed to be 1, okay? Because obviously if you integrate over the whole space or region in which the particle is found, the probability of finding it will always be 1. Okay, so then I take out a square and just multiply this. Okay, so 9 psi 0 square plus 12 psi 0 star psi 1 plus 12 psi 1 star psi 0 plus 16 psi 1 whole square. Okay, dx. Now you know that the stationary states of the harmonic oscillator are orthogonal. Okay, so we know that, okay, I'm just writing the formula. I mean writing it just mathematically. The stationary states of the harmonic oscillator are orthogonal, delta mn. So this is 1 if m equal to n, else 0. Okay, so that makes our problem easier to solve. Therefore a square 9, you know this integration over the whole space is 1, so 9 plus these will be 0, and then the last one 16, that is equal to 1. So 25 a square equals 1, therefore a is 1 by 5. Okay, so this is our answer. Then you construct psi x t, okay, and its square. So the next one is okay, so I will just add the EIT term, okay, to my existing space term. So psi xt, as you can already guess very well, that is 3 psi 0 x e minus I e1 t by h cut, or rather e0. Okay, plus 4 psi 1x minus e. Okay, so this obviously, E is equal to h cut omega. So I would just write it in terms of omega because this is the harmonic potential, the harmonic oscillator. So 1 by 5, 3 psi 0, x e to the power e minus I omega t by h cut. Okay, plus 4 psi 1 x e to the power minus 3 I omega t by 2. Okay, so now psi square, modulus of psi square, the probability density, okay. So this, again, you have to multiply. So this is psi star psi, which will give you 1 by 25, 9 psi 0 square, plus 12 psi 0 psi 1 e I omega t by 2 multiplied by e minus 3 I omega t by 2 plus 12 psi 0 psi 1 e minus I omega t by 2 multiplied by 3 I omega t by 2 plus 16 psi 1 whole square. Okay, so this reduces to 1 by 25, 9 psi 0 square plus 16 psi 1 whole square plus 24 psi 0, again using Euler's formula, cos omega t. So this is the probability density. Okay, now again the expectation value. Okay, expectation value of x and p. So I think this is part C. Okay, so what will be this? Yes, how will you go about this? The third part. as I've already told you earlier, that it will be just this, the probability density multiplied by whatever is asked of you. Okay, so that will give you 1 by 25, 9 psi 0 square dx plus 16 x psi 1 square dx plus 24 cos omega t. Okay, look at this one. X psi 0 psi 1 dx. Okay, for a harmonic oscillator, this can also actually be a problem, that x psi 0 square dx is always 0. Okay, therefore this is also equal to x psi 1 square dx. These are always 0 if you have the individual, the wave functions of just the first second order terms. So therefore for the last term, these two are already 0. Okay, now this one, how will we solve that? X psi 0 psi 1 dx. Now we will write this psi 0 psi 1. Those are the first two wave functions of the harmonic oscillator in terms of omega. Okay, so that will give you m omega by pi h cut and 2m omega by h cut x e minus m omega by 2h cut x square, and then again the second term minus m omega by 2h cut x square dx. Okay, if you just multiply these, it looks simpler. 2 by pi m omega h cut x square e minus m omega by h cut x square dx. Okay, this will give you 2 by pi root of this and m omega by h cut. Okay, whole multiplied by 2 root 2 root pi, and then again 2, then half square, half h cut by m omega whole cube. This will simplify to h cut by 2m omega, this under root. Okay, therefore our expectation value of x turns out to be 24 by 25 h cut to m omega multiplied by cos omega t. Okay, basically this term, you've just written this term, and you see outside there is this 25 and the integration of whatever came out. We just wrote that. That's it. Okay, now expectation value of p. This again m dx dt. Okay, just you do a ddt of this one, this cost term. This is supposed to give you minus 24 by 25 m omega h cut by 2. Okay, and sine omega t. All right. Okay, so I think, okay, energy. Find the energy of this particle. So what was the last one? You can see that the particle is only in the psi 0 and psi 1 states, right? So with associated with psi 0 will be E0, right? And you know it is n plus 1 h cut omega. So n0, so just half h cut omega. Okay, and E2, E1, sorry, will be again n plus 1. So put 1 in place of, okay, this is the formula. So this will be 3 by 2 h cut omega, the energies. Okay, is there any problem? If not, we'll go ahead to the next one. So two neutrons are in an infinite square well of width 2 femtometers. So what is the minimum total energy the system can have? Please think about it for a while. So hope you have understood this problem. In the previous problems we saw that we're only dealing with one particle, but here there are two particles, right? So if spin is not ignored, then both the particles can be in. Okay, here let me just write that ignore spin. So according to Pauli's exclusion principle, if this is my infinite well, okay, and you have your levels like this, right? N is equal to 1, 2, 3, 4, and so on. So you can have a spin up and spin down particle at one state, but not more than that, right? Just due to Pauli's exclusion principle. But if we ignore spin, that means one particle will be there in each state. Okay. So the first one, so two, okay, let me write it like this. The two neutrons will be in, okay, no, the first particle will be in n equal to 1, and second, first neutron, and second neutron will be in n is equal to 2. Okay, therefore what will be the minimum energy? Now you know that the equation for energy in an infinite square well is n square pi square h cut square by 2 ml square, isn't it? Therefore, oh, please excuse me. Yeah. The total energy here will be E1 plus E2. Okay, so that gives you pi square h cut square is outside, 2 ml square, right? So this gives pi square h cut square by 2 ml square, 1 plus 4, that is 5. Okay, now if you put the values of the neutrons and everything else, okay, suppose if the value of the system, say, was already mentioned as, suppose this information was given that nc square for the neutron is 939.6 MeV. Okay, so how will you include or incorporate this in this formula? Because here is no c here, right? So what we will do is just add a c in the numerator and denominator. Okay, so they cancel out, so the meaning is the same. So now we will put the value of mc square which is given, okay, and you put in the values and you will get E is equal to 255 MeV. You see, everything else is given. L is given 2 femtometers, which is 10 raised to the power minus 15. Okay, so this is what is expected to be the result. Okay, is there any problem with this problem? If not, we'll go to the next one. So here, a particle of mass m and kinetic energy E greater than 0 approaches an abrupt potential drop V0. So what is the probability that it will reflect back? What do you think this will be? So there is an abrupt potential drop. Okay. So if my potential was just like this, going straight, there is a sudden drop like this. Okay, so since it's a drop, let me give it a minus sign. So say this is my reference level, this is 0, Vx, and this is x. Okay, so my potential is this one. So you have a particle, this is my particle, mass m, this is approaching, see E is greater than 0 here, okay? So this is approaching this potential drop. So what is the probability that this will, let me see, that this will, go and then reflect back? Just an intuition, you can understand that the reflection is actually going to be very less, right? Because the particle is most expected and supposed to just fall. Isn't it like we are walking on a staircase? Who in the world reflects back? Everybody falls if you don't see the stairs, isn't it? So, but still, it's a quantum mechanical problem. There can always be, anything can happen. Anyway, so how will you go about it? And the energy is given as E is equal to V0 by 3, okay? Okay, so you can already understand this is like the finite square well potential, okay, where you have a square well like this, and say this is your v equal to 0 and this is minus v0, and you get all your wave functions of this form for x in this region, okay, region 1, 2, 3, if I say. So this is region 1, and for region 2 you have psi x equals c sine lx plus d cos lx, and region 3 you have f e kx. Okay, this is x greater than a. Once again, I'm not going into the derivations. Okay, where L is equal to 2me plus v0 by h cut, and your k is equal to 2me by h cut. Okay, so in this problem you can see that we don't have region 2. Okay, so we won't be using both the sine and cos terms. So for x less than 0, we have psi x. We'll just use the Euler's formula, ikx plus be minus ikx. Okay, and for x greater than 0, we have psi x equals say feilx. Okay, now according to the continuity of the wave function, whatever is the wave function here will be the wave function just close to it, right? So we will equate these two. So due to continuity of psi, we will have a plus, if you call it as psi 1 and psi 2, basically psi 1 equal to psi 2. Okay, so you will have a plus b equal to f at x equal to 0. Similarly, due to continuity of the first derivative, we will have ik a minus b is equal to ilf. Okay, so now you know that the reflection coefficient r is given by b by a whole square. Okay, because you can see that B is in one direction and A is in the other direction, right? So just the ratio of these two. So what will that be? Okay, from these two equations, from equation 1 and 2, we get A plus B is equal to K by L A minus B. Okay, that will give you, if you take the A terms on one side and the B terms on the other, you will get something like this. So B by A equals minus 1 minus K by L by 1 plus K by L. Okay, therefore the reflection coefficient is B by A whole square. So L minus K, basically this one, whole square. Okay, so let us put the values of L, this one, L and K. Okay, we'll just put these values and we will get something like this. By E plus V0 plus root E. Okay, we know that E is equal to, it is given that E is equal to V0 by 3. So we will try to bring it in terms like E divided by V0 or something. Therefore, R is equal to, let us divide both the denominator and the numerator with E. That will give you 1 plus V0 by E minus 1. Okay, divided by 1 plus V0 by E plus 1. So let us put the values. V0 by E, this will be 3. So 1 plus 3 and then minus 1. Again 1 plus 3 plus 1 whole square. This is supposed to give you 1 by 9. So I think our intuition was almost correct. See, the reflection coefficient is just 1 by 9. So the transmission coefficient is 8 by 9. Okay, so most of it will obviously pass, fall down. Very little of it will be reflected back. Okay, so if there is any problem in this, let me know or we'll end the class here. So if not, we will end the class here. So thank you so much for joining today and attending my class. If there is an issue with any of the problems, please let me know in the next class. That is why I'm here. Like, that is my purpose of taking these classes. Okay, so bye bye. Have a nice evening.
Thank you. Yes.